Okay, good morning, everybody. Welcome back to this AstrotwinColo School of 2020. We are starting our fourth day with Professor Aurora Caselli. Thank you very much for attending, and thank you very much, Aurora, for being here with us.
All right, great. So today we are starting the fourth day of lectures, and what we'll be talking about today is the radial velocity and how high-resolution spectroscopy is the best way to get radial velocities. And then we'll also talk about why radial velocities are important, what type of science you need that you'll do with radial velocities. Okay, so I will share my screen to start.
We can create a workbook that says if contacted industry A and downloaded form B, then move them to this industry automatically.
Okay.
Or yeah. We'll walk before we run.
Great. So like I said, today we will be talking about applications of high-resolution spectroscopy and in particular radial velocity. For most of the class, we'll talk about radial velocity, and maybe for the last little bit, we'll start talking about exoplanet characterization, and then tomorrow we'll finish talking about exoplanet characterization and a few other applications that are good for high-resolution spectroscopy. So to start, any system that is in a binary, so either two stars or a planet in a star, is going to be orbiting a center of mass. So usually when we think of an exoplanet orbiting a star, we think of the star is still and the exoplanet is just going around the star. But in reality, both the exoplanet and the star are orbiting the center of mass. And this becomes a lot more clear when you're talking about binary star systems, when the stars are more equal in size. So this animation here is probably something more like a binary star system where one star is a lot bigger, because you can clearly see that they're both orbiting the center of mass. And the center of mass is given by the masses of the two objects. So here's kind of a animation or just a diagram that's showing that. So if you have one mass that's bigger than the other mass, the center of mass is going to be closer to that bigger object. So the distance between the center of mass and the center of the object times the mass is equal to the distance of the second to the second object, the center of mass, times that mass. So as you can see, as the mass gets larger for M1, the distance has to get smaller, and vice versa. So if M2 is smaller, then the distance to the center of the mass is larger. And you can also talk about this with velocities. So as M1 is larger, it's going to have a smaller velocity. And as M2 is smaller, it's going to have a larger velocity. So in exoplanet systems, even though the central star is orbiting the center of mass, the center of mass is very close to the center of the star. And so the velocities are very small compared to the velocity of the planet. In a binary star system, we kind of get more equal masses and velocities. And so you can it's much easier to resolve both of the velocity components in a binary star system. And so since we're interested in discovering the masses of these planets or stars or binary stars, we need to know the velocities. And if you remember from last time, we talked about the Doppler effect. And so just as a reminder, the Doppler effect basically allows you to resolve velocities of stars or any objects, because as an object emits light and is moving either towards us or away from us, the light gets redshifted or blue shifted. And so we can resolve these velocity changes in the star, or in the host star, or in two binary stars. And we can measure the velocities of these stars, which then allows us to measure the masses because of the center of mass equation. So to show you an animation that kind of shows how we actually resolve the radial velocity positions, there's a nice video here. So this is just showing the light from the central star is shown here. The light from the exoplanet is not shown. And so you can see that as the star moves towards us, you're going to be having the light being blue shifted and the lines being blue shifted. And as the star moves away from us, I'll play this again. As the star moves away from us, the lines are going to the red. As the star moves towards us, the lines are moving into the blue. Now the lines are starting to move back into the red. And so by measuring the shifting positions of the absorption lines, we can determine the radial velocities, which then allows us to determine masses. Okay. So first I wanted to talk about binary star systems because it's a bit easier to think about binary star systems because you actually have two stars orbiting each other, and you can measure the radial velocities from both stars. So here's a plot from a paper where they measure radial velocities from a primary star and a secondary star. So in blue, you can see the radial velocities are plotted. And what they do is they take measurements at each of those, these times of the radial velocity shift at that exact time. And they do this for both the primary star and the secondary star. And the primary star is the star that has a larger mass. And the reason that we know that this star has a larger mass is because it has smaller radial velocity shifts. So you can see that the primary star, the curve here looks a bit more shallow. And if we go back to our center of mass equation, the star that has the smaller velocity is going to have the larger mass. And then we have our secondary star, which has larger velocity shifts. But these stars probably are pretty similar in mass because the velocities are pretty similar. You can see that one goes to about we start at minus 50. So one goes about 50 kilometers per second, and one goes about 100 kilometers per second. So they probably have a change in about a factor of 2 between their masses. And if we can measure the radial velocity shifts of both stars, we can determine the masses and the orbital velocities of both stars. And this is especially cool for eclipsing binary stars. So when we have two stars that are not only orbiting each other, but orbiting each other in an orientation where we can see one pass in front of the other. So then we can get light curves where one star passes in front of the other, and we can get radial velocities. And by getting both the light curves and the radial velocities, we can measure the masses and the radii of both components for the stars. And this is extremely important to do for stars because it's the best way that we really get, we can really calibrate relationships between properties that you can easily measure, so like spectral type or color, to physical properties like mass and radius. So it's really, really difficult to look at a star and know its mass or radius because the radius is, the stars look like point sources on our detector. We can't actually resolve the radius of the star. And the masses are difficult to measure. And so we know that the mass kind of sets many of the physical properties of a star. And so in order to guess the mass we need to be able to have a relationship that turns something observable, like a spectral type, and then say, oh, this star is an M4 spectral type. It probably has this mass and this radius. And also, this is really important because we can check stellar evolution models. So all of the modeling that we do for stars that helps us determine what type of star it is, how long it's been living, and all of those properties are based on stellar evolution models. But stellar evolution models need to be calibrated. We need to check that what we're putting in, all the physics we're putting in, is giving us the right answer. So here's a plot, again, by the same paper. This is showing low mass stars. So get the cursor so it doesn't. Okay, this is showing low mass stars from masses of about 0.25 times the mass of the sun up to about 1.5 times the mass of the sun. And also their radii are plotted on the same plot. And you can see that we have lots of different models. The models are all plotted with different lines, and the observations of these different eclipsing binary stars are shown with the dots. And so originally, some of these models for low mass stars showed that their radii were much smaller than what we were measuring. And so when we started measuring more accurate radii, the models had to add some correction factors because they weren't getting the exact correct radii for the given masses. And so this is really important work to do for stellar physics. Okay, so radial velocities, you can do the same thing for detecting exoplanets. So here, we're not going to be able to detect the lines of the exoplanet. We can only detect the lines of the primary star because the primary star is just so much brighter than the exoplanet. But by measuring the radial velocity shift of the star, we can infer the presence of the planet because something has to be causing the star to move around the center of axis. There has to be another mass there. And by looking at the size of the star's wobble or how much it's moving, we can figure out the mass of the planet that's perturbing it. So this is example data of the first exoplanet discovered, 51 Pegasi, that was discovered with this radial velocity method. So it kind of shows a similar graph like we saw for the eclipsing binaries, but instead of having two stars, again, we just have the radial velocity curve from the host star. And I wanted to just make sure that that we remembered whenever we talk about radial velocity, we can only resolve radial velocities, or we can only resolve velocities that are in our line of sight. So radial velocity only works for things that are moving towards us and away from us. And so oftentimes we're not actually resolving the true velocity of the system, which means that we're not resolving the true mass of the system, because we have this inclination factor. So planets that are in this face-on orbit, none of the velocity is moving towards us or away from us. And so they're basically undetectable. And if we have a system that's in an edge-on orbit, all of the motion, almost all of the motion is towards us or away from us. And so then the mass that we actually do measure is the true mass of the system. But if we have something in between, we probably will be able to detect the planet, but the mass that we have is not the true mass of the system. It's a lower estimate on the mass. And also I wanted to bring up this nomenclature that I'm going to be talking about and that you'll see a lot of the plots have on them, which is the phase. And so as the exoplanet or the star or the binary star system orbits the center of mass, we call this different phases. And so as the planet passes, or the secondary star passes in front of the primary star, we get a transit if it's in this edge-on orientation. And this is what we call a phase of 0. So at the center of the transit, this is phase 0. And as the secondary star, or the exoplanet, passes behind the host star, this is usually at a phase of 0.5, although it can be slightly different if we have an eccentric orbit. And so oftentimes you'll see plots like this, where people who've made the plot have phase folded. And so you have observations spanning years of time, but once you find a period, you can put them all onto the same plot, putting their phase from 0 to 1. Okay, so I've kind of hinted at some of this stuff, but there are a bunch of properties that you can derive from radial velocity measurements. So this plot here is just kind of a easy schematic of what your radial velocity measurements will look like. So we have velocity on the y-axis and either time or phase or something like that on the x-axis. And so we'll be taking radial velocity data points throughout this time period. And when the host star, is at its maximum, and then goes through the minimum and then back to the maximum, that is one orbit. So the star has gone through one orbit, and so that is the period of the planet as well. The star and the planet are always opposite each other in the center of mass. And so this maximum to maximum tells you the period of the planet. Okay, so then you can apply Kepler's third law, which you probably remember from your introduction to astronomy classes, that relates the period to the semi-major axis of the planet's rotation period. And so for a sun-like star, the third law says that the period squared is equal to the semi-major axis cubed. And this relation can be scaled for different types of stars by adding an extra mass of the star factor here. And for this equation to work, you also need to have the period in years and the semi-major axis in AU. Okay, so next, once you have the period and the semi-major axis of the orbit, you can calculate the velocity of the planet. And so if this is just a simple circular orbit, the velocity is just the circumference of the circle divided by the time. But if you have a more eccentric orbit, you're going to need to plug this into the elliptical equation and have a bit more of a complicated thing. But again, you still just need to find the circumference of your ellipse and divide by the time to get the velocity of the planet. Then the velocity of the star can be found from this diagram. So this K here is labeled, and this is the semi-amplitude of the star's velocity. So this tells us the maximum velocity of the star as the star is moving either fully towards us or fully away from us. So if the star is in a perfectly edge-on orbit, this semi-amplitude here is the velocity of the star. However, since if we don't know the inclination of the star, this semi-amplitude is not going to give us the full velocity. So you need to add this sign of the inclination here. And so the star's velocity is given by the semi-amplitude times the sine of the inclination. And then lastly, you can plug these things into the center of mass equation and find the mass of the planet. But because we still have this sine of the inclination from the star's velocity, if we don't know the inclination of the system, we're going to get the mass of the system times the sine of the inclination. And lastly, you can also get the eccentricity of the orbit. So for different eccentricities, the curve will not look quite as normal and sinusoidal. So maybe it'll peak like this, and then it'll go down for a really long period of time and come up. But basically, you can fit the shape of the curve in order to figure out the eccentricity of the orbit. And I just wanted to remind you also that radial velocities do not give you the size of the planet. The size of the planet has nothing to do with the center of mass equation. If you remember, it was just the mass that tells you how far away it is. So if you have a really puffy planet that's not very dense, and you have a very dense but small planet, those are going to give the same radial velocity changes in the star. And so you won't be able to tell the difference between those. But if your planet transits, by combining with the transit, you can tell what the inclination is. The inclination has to be almost edge on for a transit. And so then you'll get the true mass of the planet. And also, like eclipsing binaries, you'll also get the true radius of both of the stars and the true masses of both of the stars. And for exoplanets, you'll get the true mass of the planet. And also, you can now combine the radius of the planet, because for transits, the transit is given by the radius of the planet. The transit depth is given by the radius of the planet. And so you can combine this mass and the radius actually to get some information about the density or the physical characteristics of this planet. And by knowing the density, there's lots of things that you can determine, like, is it a rocky planet? Is it a gaseous planet? Is it a water world? And so that can really start to tell us a lot of information about these planets. Okay. So now that we've kind of gone through what radial velocity measurements entail and what information you can get out of radial velocities, I thought we would talk about what planets give different radial velocity shifts in order to really show you why high-resolution spectroscopy is really necessary in this field. So this is a paper from Deborah Fisher in 2015, and she calculated what the K1, if you remember, K is the star's semi-amplitude in the velocity. So this is telling us what's the maximum velocity shift that the star is going to have. So for a Jupiter type of planet at 0.1 AU, so this is really close, we're going to see a velocity shift of about 90 meters per second. If we put Jupiter at its true orbital distance in the solar system, which is about at 5 AU, we see a velocity shift of about 12 meters per second. So now if we want to measure, if we want to detect a Neptune-sized planet, Neptune is smaller in mass, even if we put it at 0.1 AU, it's only going to have a velocity effect. The star is only going to be shifted by 4 meters per second, or about 5 meters per second. So now moving down to even lower masses, if we want to detect a super Earth, so 5 times the mass of Earth at 0.1 AU, we're going to be able to need to measure radial velocities with 1.4 meters per second. And that's at 0.1 AU. If we go out to 1 AU, which is the distance where Earth is, we need to be able to measure 0.45 meters per second. And lastly, if we want to measure an Earth-sized planet at a very close distance, we need to be able to measure 0.28 meters per second. But an Earth-like planet at an Earth distance, we need to be able to measure 0.09 meters per second. And so oftentimes you'll hear people say, we need to be able to measure 10 centimeters per second radial velocity shifts. And this is really small. Centimeters per second radial velocity shifts on stars that are not our sun. Even just thinking about it, it seems really, really difficult. Basically impossible. But we'll talk about later what we've been doing to try to do this. And so all these values, remember, are for sun-like stars. But if we go to lower mass stars, because the star's mass is smaller, the center of mass will be farther away from it. And so we can resolve these type of planets will have will have larger velocity shifts if the star is lower mass. Okay. So it's not surprising that we have a bias in our radial velocity detections so far. So I pulled this from the NASA Exoplanet archive a few days ago on November 10th, you can see. And so as of November 10th, 821 planets had been discovered by the radial velocity technique so far. And so on the x-axis, I'm showing the orbital period of the planet in days. And on the y-axis, this is the planet mass, if it's available, or the planet mass times the sine of the inclination. So if these planets are not transiting, we only have the mass times the sine of the inclination in Jupiter masses. And so you can see that we have a huge bias to detecting planets with larger masses. And so that's why we have so many more points up here. But you can see that we actually are starting to be able to detect lower and lower masses. These are all kind of newer planets, and our newer instruments that we're building to detect these are working. And so eventually we do want to start to be able to detect. You can see that as we go to the lower masses, we are going to shorter distances. So as we move to lower masses, in order to detect an Earth mass planet, it's still easier to detect it at a smaller orbital distance. And so we are only able to detect so far for the lower mass planets, the planets at closer orbital distances. But hopefully with our new instruments, we'll start kind of filling in this part of parameter space down here. Since to detect an Earth-like planet in the habitable zone, we kind of need to be filling in something over here. Okay, so to do all of this, to measure centimeter per second radial velocity precisions, we need to have a spectrograph that has good radial velocity, that has good spectral resolution. So if you remember, the spectral resolution is the wavelength divided by the change in the wavelength. So we want the smallest possible wavelength shifts. And so we can relate this to the radial velocity. So the speed of light divided by the radial velocity change. So in order to measure centimeter per second precision, you need as high radial velocity, you need as high resolution as possible. So kind of the highest resolution spectrographs that we currently have a resolution of 150,000. So if you plug this into our equation here, this only results in a pixel size of about 2 kilometers per second, or maybe a little bit lower than that. But we need centimeter per second precision. So you might be saying, okay, well, this is impossible. But we have some techniques for how to do this.
Hi, Aurora. Sorry to interrupt.
Yes, I see.
You have some question in the chat. Is there a way to know the inclination in some systems?
Yeah. So the easiest way is if the system is transiting. If the system is transiting, then we know that the inclination of the system has to be close to 90 degrees. And we can actually fit the shape of the light curve of the transit in order to pull out the exact inclination. For other systems that are not transiting, it's a lot more difficult. So sometimes, in some cases, we can figure out the inclination if we have a giant planet, and we can detect the giant planet in other ways. So I'll kind of go into how we can directly detect the planets in other ways. But for non-giant planets that are not in transiting systems, it's it's really difficult to know the inclination, so to know the true mass. So yeah, it's not really possible. Maybe combining another technique. Yeah, I'm thinking maybe like combining direct imaging, if you can directly image it, or emission spectra or something. But it's not easy to get the inclination if the system's not transiting. Okay, so like I said, our width of our pixels are about 1 kilometer per second, but we want to get centimeter per second precision. And so from a single line, the precision of your radial velocity is set by the full width at half maximum of your line, which is set by the width of your spectrograph, or the broadening of the line.
Excuse me, Aurora.
Yep.
You have a second question. How do we know from the radial velocity curve that the system has multiple planets?
That's a great question. Yeah, I kind of glossed over what happens with multiple planets. But basically, in our nice plot like this is a single planet system. There's a single radial velocity curve. But in a system that has multiple planets, it would look a lot messier. So you might have, what happens is you get basically 2 radial velocity curves added onto each other. And maybe I'll look for a image that shows this after the break so I can show you what it looks like. But basically you might see like a large trend or something like this, with then a smaller trend on top of this. So maybe you would see like a short period planet with a smaller trend, and then a long period planet here. And what people do is they take a Fourier transform. And a Fourier transform basically just looks for sinusoidal shapes in your in your radial velocity data. And then it tells you what are the most likely periods of the sinusoids in that data. So then what people do is you plot up your data and you find the most likely period. And then you remove that and see if you can now see a smaller trend in the data once you've removed your first planet. And then you can kind of do that over and over again and see if you can find multiple planets. That's a good question. Maybe I will look for a plot that shows that. Okay, right. So I was saying that the radial velocity precision that you're going to get from a single spectral line has to do with the full width at half maximum, so how wide your line is. And so this is dependent on the instrumental broadening and then how broad the line is anyways. So this is harder to do with lines that are broadened by, say, rotation or something. Divided by the contrast. This is just how deep the line is and the signal to noise of your data. So that's for a single line. And so you can kind of, if you plug in some numbers here, you'll see that it's impossible to measure centimeter per second precision with a single line. But if I combine the measurements of thousands of lines together, we can start to reach a precision of about 1/1000th of a block velocity pixel. And this is kind of the precision that we want to get to be measuring an Earth-like planet around a sun-like star. And we need lines that are, in order to measure these radial velocity precisions, some lines are better than others. So we want lines that are naturally deep, but also narrow, so they're not as dependent on different broadening mechanisms. And so what people have found is that iron lines are really good for this, because iron lines have tons of lines in the optical, and they have these very deep, narrow lines that are not affected very much by pressure broadening or other types of broadening. Okay, so to combine the measurements from thousands of lines together, we use the cross-correlation technique. All cross-correlation does is you can kind of think of this as sliding one spectrum across the other spectrum and multiplying it by the other one. And where the two spectra line up perfectly, you get a peak in the cross-correlation function. So here we have, pretend we have the data in blue. Here's our blue data. And here in green, we have our green model. So we're slowly sliding the green model across the data. And now if we look over here in our plot, you can see that we get to a minimum when they don't match at all. And now when we slide back, they don't match at all, we get a minimum. And then when they match perfectly, we get a maximum in the cross-correlation function. And so this is what we do in order to combine the measurements of thousands of lines together. So showing you a bit more what this looks like in practice. Here we have our star spectrum. So we have the wavelength and we have the counts. And here we have a model of all of the iron lines. And like I said, iron lines are really good for this because you can see how many lines there are and how narrow and deep they are. So we're going to slide the iron line across the star's spectrum. And this is what we get. This is what the cross-correlation function shows. So unlike in the previous slide, where we have multiple peaks because we're kind of sliding back and forth, there's one peak where the two match perfectly. And so this peak now gives me a measurement of the radial velocity with a much smaller precision than I would ever be able to get from a single line. So by doing this cross-correlation and then measuring the radial velocity peak, so then you record the peak of this function, and that is the radial velocity for one spectrum. So that's one of these data points. Then you have to do this hundreds of times in order to fill out this radial velocity curve here. And so you can see finding planets with the radial velocity technique is extremely time intensive, and you need the best high resolution spectrographs as possible. Okay. So in order to come with, to be able to measure this centimeter per second radial velocity precision, we also have to talk about the sources of noise that are present in the data. So there's both sources of noise that are astrophysical and sources of noise that are instrumental. So we'll go through kind of the main astrophysical sources of noise, and then I'll briefly touch on the instrumental sources of noise. So the astrophysical sources of noise that we're going to talk about are stellar pulsations, granulation, and star spots and magnetic activity. And for instrumental noise, there's the wavelength calibration. So this is what we talked about 2 days ago. On Tuesday, we talked about how you have to take these wavelength calibrations and how if you need to have very high wavelength precision, you're going to use one of these arc lamps. And so definitely for this high precision radial velocity, you need to use some of these arc lamps. You can't just use the sky lines for your wavelength calibration. And then also there's instrumental effects like we talked about also 2 days ago with thermal mechanisms in the spectrograph changing very slightly. If they change very slightly, you can get a very slight offset in the like where the CCD is sitting, and you can get very slight changes. And if for some reason, this slightly changes over time and slightly increases, you can start to trick yourself into thinking that you have an increasing trend in your radial velocity data, when in reality, you just have something in your spectrograph that's causing this increasing trend. And also, variations in the index of refraction of air on a nightly basis can cause jitter in your radial velocity measurements. Okay. So for the astrophysical sources of noise, the first one that we'll talk about is stellar pulsations. And all stars have some pulsations because they are giant balls of gas and plasma. And as pressure moves through them and sound moves through them, they're going to pulsate a little bit. And this is not related to radial velocities, but you can do, this is how we do astroseismology, by looking at these pulsations of the stars. But these pulsations also cause meters per second variation on most stars, and can cause up to kilometer per second pulsations on some of these pulsator stars. So this is a video of this particular type of pulsator. It's called a delta Scuti pulsator. So I don't have the sound going, but I just wanted you to look at this artist's impression of what a delta Scuti pulsator would look like if we were looking at it up close. So you can see it gets brighter and dimmer, and then maybe the top half gets brighter and the bottom half gets dimmer, and then the bottom half gets brighter and the top half gets dimmer. And all of these brightenings and dimmings are causing radial velocity jitter for these stars on the kilometer per second, with velocities of about kilometers per second. And there are some exoplanets that have been found around these type of delta Scuti pulsators, and it has made it much more difficult to characterize the exoplanets that have been found around them. Actually, the star that we have been looking at, WASP-33, where we looked at the rotational broadening, is a delta Scuti pulsator. And so because WASP-33 is such a big planet, we still can measure the radial velocity shift of the star. But if the planet was much smaller, we would not be able to measure the radial velocity shift of even this hot Jupiter type planet, which are the easiest to measure. Okay. And so next, this is more, granulation is more for sun-like stars, because the sun-like stars have convective exteriors. And on the surface of the sun, this is the surface of the sun. Here's a video that's showing the convective cells basically on the surface of the sun, where you have hot material rising up and cool material sinking in. And you get this all kind of changing on the surface of the sun. And so because you're having hot material coming up and moving towards us and cool material moving away from us, this causes changes in the radial velocity. And because there's so many hot cells and so many cool cells, it doesn't cause any net shifts in radial velocity, but it does cause like meter per second jitter on the radial velocity over time, as we get sometimes with more cells moving towards us and sometimes with more cells moving away from us. Okay. And one of the biggest things that's a problem for radial velocity precision is starspots. This is really the biggest problem because a lot of the low mass stars that we really are interested in, because it's the low mass stars that will allow us to detect Earth-like planets in the habitable zone. Low mass stars have a lot of star spots on them. And this plot here, I thought is really nice. It basically shows what happens as a star spot moves into your line of sight and moves away from your line of sight. So on the bottom, this is a model of what a single absorption line would look like. And as the star moves into our line of sight, we get less flux on the blue side of the absorption line. And then as the star spot moves away and out of the line of sight, we get less flux on the red side of this absorption line. And so if you then try to measure the radial velocity, I wonder if I can get it to stop. When the spot is over here, you're going to measure the center of the radial velocity a bit on the bluer side. But when the spot is over here, you're going to measure the center of the radial velocity a bit on the redder side. And so you get these changes in radial velocity on the same orbital time period as the change, you get the changes in radial velocity looking like a periodic pattern at the rotation period of the star. And so for some stars, this can cause radial velocity changes of 1 kilometer per second, which is huge and a huge problem. For most stars, it's more like 1 meter per second. The stars that are more likely to be affected by star spots are younger stars. So stars that are less than 1 billion years old, and also cooler stars, like I said, so M dwarfs. And this makes confidently detecting radial velocity planets around young M dwarf stars really difficult. And this is a very active area of research. There is lots of research being currently done to figure out how to mitigate effects from star spots. Because like I said, on young M dwarf stars, this makes finding planets almost impossible. But even on solar-like stars, on the sun, at high points when we have large star spots, this can still cause meter per second variations. And if we are looking for centimeter per second variations, this can be a big problem. So there's lots of techniques that people are using to try to figure out where the star spots are and then to correct for this. So if you're interested in this, yeah, there's lots of papers and lots of things that people are doing. Okay. And then quickly to talk about instrumental noise. I don't want to go into too much detail about this, but the main sources of noise, in order to try to reduce instrumental noise, we want to try to have as few moving parts as possible on the spectrograph. So we don't want to be having mirrors moving in and mirrors moving out and changing slit sizes and stuff. We want to try to have as stable of instrument as possible, because that allows for less changes in, say, if you need to move the mirror in and out all the time, you can move it in and have it at a very slightly different position, which would then cause a change in the radial velocity that you would measure potentially. You also want to keep the instrument at a constant temperature, at a cold temperature. So any fluctuations in the temperature can cause extra dark current and changes in the index of refraction of the air, which can then cause changes in the radial velocities. So a constant temperature and a cool temperature. And next, the lamps for wavelength calibration. You need to make sure that these are stable over really long periods of time so that accurate wavelength solutions can be determined over years of baseline. Another thing that you have to think about is, in order to measure the radial velocity of an Earth-like planet around a Sun-like star, you need at least a year of baseline, because the period of the star for a planet that orbits in a year, the star is also going to be orbiting in a year. And so you need at least a year to measure an Earth-like planet around a Sun-like star, and probably significantly more, because you probably want at least 2 rotations, 2 full periods to determine that the planet is actually really there. And so that means that these instruments, they have to be stable for years on end. And specifically talking about the calibration lamps, calibration lamps can show drifts in radial velocities on the centimeter per second over years, which mimics the signal of an exoplanet for a year. And so you have to make sure that you are testing these frequently, making sure that they're staying stable, and having really high quality materials that you're using for these instruments. Okay, so next I wanted to talk about characterizing exoplanets at high resolution, but I was thinking I would save this next part for after the break. So is it okay if we take our break 10 minutes early, Esteban, if there's no questions?
Yeah, absolutely. There is no problem. And so far, there are no more questions on the chat, so it's okay. So the idea will be we have the break until 9:15, but if we are doing it a little bit early, we can go back at 9:05, so 3:05 or your time.
9:05 is perfect.
9:05 here, 3:05 your time. So let's see again in 15 minutes. Okay, perfect.
Okay.
Okay, bye.
Thank you.